Hello, welcome to our short video on how to design a low noise and long range PIR sensor conditioner circuit. This schematic represents a low noise and long range passive infrared sensor or PIR sensor conditioner circuit. The circuit is composed of two gain stages to amplify the output signal of the PIR sensor. Multiple low-pass and high-pass filters are used in the design to reduce the total noise at the output of the circuit, which allows for motion detection at long ranges and reduces false triggers. This circuit can be followed by a window comparator circuit to create a digital output. The design goals for this circuit is to have an AC gain of 90 dB with a lower cutoff frequency of 0.7 Hz and an upper cutoff frequency of 10 Hz. The circuit is designed to use a single 5-volt supply. The first design step is to calculate the components for the RC low-pass filters to set the lower cutoff frequency, or F sub L. The low-pass filters are formed using the resistors R1, R6, and R11, and the capacitors C1, C5, and C9. Since there are fewer standard value capacitors, we will select the capacitors first and then calculate the required resistor value to set the cutoff frequency. We will choose C1, C5, and C9 to be 10 microfarads. The resistor values can now be calculated using the equation 1 divided by 2 times pi times F sub L times C1. Using this equation, we calculated the resistor value to be 1.592 kiloohms. The next closest standard resistor value is 1.5 kiloohms, so we will use this value for the design. Next, we will calculate the components for the RC high-pass filters to set the upper cutoff frequency, or F sub H. The high-pass filters are formed using resistors R4, R9, and the equivalent voltage divider resistance of R2 in parallel with R3 and R7 in parallel with R8, along with capacitors C2, C3, C6, and C7. We will choose to use a capacitor value of 33 microfarads. The resistor values can now be calculated using 1 divided by 2 times pi times F sub H times C2. Using this equation, we can calculate the resistance for R4 and R9 to be 6.89 kiloohms. The next closest standard resistor value is 6.81 kiloohms, so we will use this value for the design. For the voltage dividers, the equivalent resistance is half of the resistor values in the divider. Therefore, we must select the resistors of the voltage dividers to be double the calculated value. This yields a resistance of 13.62 kiloohms. The closest standard resistor value is 13.7 kiloohms, so that is the value we will use for R2, R3, R7, and R8. The next step is to set the gain of the circuit. Since this circuit uses two gain stages, we will divide the total AC gain equally between the two stages. Therefore, each gain stage must have a gain of 45 dB, or 177.828 volts per volt. The gain of the first stage amplifier is set using resistors R4 and R5, and the gain of the second stage is set using resistors R9 and R10. The AC gain of each stage is equal to 1 plus R5 divided by R4. Rearranging this equation, we calculate R5 to be 1.2 megaohms because the value of R4 was previously set to 6.81 kiloohms. The final step of the design is to calculate capacitors C4 and C8 in the feedback of the op-amp, which help reduce the noise of the circuit by limiting the noise gain of the amplifier. The capacitance is calculated using the equation 1 divided by 2 times pi times F sub H times R5. The calculated capacitance is 13.263 nanofarads, so we will use the next closest standard capacitor value, which is 15 nanofarads, in this design. Running an AC sweep analysis, we find that the maximum AC gain of this circuit is 78.88 dB. The AC gain of this circuit does not quite meet our design goal of 90 dB because the poles created to limit the upper and lower cutoff frequencies occur before the gain reaches 90 dB. To increase the AC gain, the pole location would have to decrease for the high-pass filters and increase for the low-pass filters. This, however, will increase the noise of the circuit because the bandwidth increases. Given this trade-off, we decided to leave the gain as 78.88 dB. Performing a noise analysis on the circuit, we see that the total noise of the circuit is 10.29 millivolts RMS. One could increase the gain of the circuit if more noise is acceptable in the design. When designing a low noise, long range PIR sensor conditioner circuit, there are a few design notes to be aware of. First, be sure to use 2 or more amplifier stages to allow for sufficient loop gain. Next, additional low-pass and high-pass filters can be added to further reduce noise. Finally, RC filters on the output of the amplifiers are required to reduce the contribution of the intrinsic noise of the amplifier. Texas Instruments has many online resources to help you design circuits with op-amps. This includes reference designs and guides, educational videos, simulation and prototyping tools, support resources, and search tools. Thank you for taking the time to watch this short presentation on how to design a low noise, long range PIR sensor conditioner circuit. Please visit www.ti.com for additional information and resources.